The first way that this applies to us is in what we call end-to-end representation learning. So the first example of this is how do we input matter into machine learning algorithms, right? Traditionally, this has been called structure property relationships in the physical sciences. This is how do I connect the structure of a material, the structure of a molecule with its properties, and its mirror image in learning is representation learning, right? What is the type of transformations that we need to apply to our raw input so that it becomes a vector that we can do learning over? Traditional approaches have worked well at this to some degree, particularly because data sets were typically small and not as big as the places where one uses deep learning typically. But as we've moved into the last few years, the libraries have become big enough where we can try to do representation learning over the full chemical space and abandon hand-engineered features, just like machine vision community did years ago, where they moved to just convolutional neural networks that are really deep and learn to process pixels all the way up to full images. We can do the same thing over atoms. And the architecture that does this for matter these days is graph convolutional neural networks. You've got a little diagram there. Essentially, they aggregate information across local graph environments such that they learn how to represent every atom optimally for a given task.